Alright, so today I'm going to show you guys a quick and dirty setup on an internal flow analysis for an axial flow pump. This is the part that I want to analyze, and I'm just really interested in seeing like turbulence within the pump, pressure. We're going to do an equation goal to measure the thrust, and yep, so here we go. I got this stuff. I'm going to just show you the impeller, because the first thing you need to do is to create a rotating region, which in this instance is just going to be a cylinder that encapsulates the impeller. If you want to know why you need to do that, it's out of the scope and scale of this, but so there's an example. As you can see, all of the impeller blades are encapsulated, so I have my rotating region. Next thing that I need to do is, as you can see here, to do an internal flow analysis, you need to have like a watertight object. So what we're going to need to do there is to create lids. You can use the lid tool, but I prefer to just do it manually, so I'm going to unhide these lids. And boom, they're just three little extrusions that cover all of the holes to make a watertight component. So as you can see now that we have section view here, everything is lidded off like there. No water's getting out of there. So now we can go over our flow simulation tab, go over to the wizard, and you can just name it whatever, and then click next. Now here you change your unit system. The only thing that I usually change with this for like a general study is the loads in motion. I like to use RPM instead of rads per second for angular momentum, or angular velocity. So you can go down here under loads in motion, go down to angular velocity, change it to RPM if you so choose, and next we're going to be doing an internal flow analysis. So I go over here, change that to internal. And then this is a very important step. If you're trying to do a flow simulation with a spinny thingy, in this instance this impeller, you're going to want to check rotation, and then you're going to want to go down here and change the type from averaging to local regions sliding. And it's going to say you have to enter a time dependent thing jiggy. It's going to say it's going to turn it on. So we're going to go over here, and this is just pretty much asking like, hey, how much time in the real world would this thing be spinning? So I'm just going to set it to 2 seconds because I don't want to process for ever and ever and ever. I'm going to uncheck exclude cavities without conditions. Leave that unchecked. Go to next. We're going to check out our fluid, which in this case is going to be water. Water. Bear with me, I'm using my little mouse pad thing because I'm out here in the woods and it sucks. I'm interested in cavitation, so I'm going to check that box. Go to next. You can change the roughness if you're like simulating a 3D printed part, for example, 20 microns is 0.2 millimeters. So that would be a good way to factor that in. And then from here, this is all going to be standard, regular, degular. Cool. We have this stuff here. We can go to check geometry, and then you can go ahead and remove any components that aren't in the study here. I've got a bunch of hidden parts because this is a larger, it's a larger assembly, but I'm really interested in checking out this part of it. So we're going to go to check, make sure that it's watertight. Cool, successful. It'll show you the fluid volume if you like. I'm going to apply that to project. You can scroll down, show your fluid volume. Sweet, that's the area where fluid's going to be. Awesome. Okay. Now, first things first, we're going to insert our rotating region. So right click on rotating regions, and then select that cool little cylinder that you made earlier that encapsulates your spinny thingy. You're going to see that you have a directional indicator here. That indicates which way the fluid is revolved around the geometry, which you can interpret as which way the spinny thingy is spinning. Mine spins at 30,000 RPMs. So as you can see, if I can find my mouse pointer, when I select that, it's currently rotating clockwise. If for some reason I need that to rotate counterclockwise, I just go over here and add a negative sign to whatever value I have, and now you can see that it changes the direction accordingly. So positive and negative value equals clockwise or counterclockwise. I want clockwise, so I'm leaving it positive. Sweet. Boundary conditions, right click. This is essentially telling SolidWorks, hey, we are determining where the fluid comes in and where the fluid comes out. What has contact with the fluid? The orifices. First I want to hide this rotating region because it makes things way easier, so I'm going to right click, hide that little bastard. Back over to Flow Simulation, boundary conditions, right click, insert boundary condition. This is very important. I usually do a cutaway. You can also use the selection manager to select the inside faces, but when you select the face, say like for example we want to select this lid for a boundary condition, you can't select the outside of the lid. Don't do that. You have to select the face that is in contact with the fluid. So for in this example, it's going to be right there. We're going to go over here to type. We're going to select environment pressure from this secondary box here, pressure openings, and we're going to select OK. Cool. All right. Capisco? Awesome. Fantastic. Beat it, fly. We're going to go to right click again and insert a new boundary condition, and then we're going to select this inside face over here, and we're going to also select environment pressure, and that's cool. This little opening up here, I'm not messing with. It's a pretty small port, doesn't significantly impact the performance of this thing. It's a water cooling port. So from here we're going to go and select goals. Right click on goals, insert surface goal. So now this is, just kind of pick your poison, whatever you want. I'm really interested in mass flow rate and velocity from the nozzle. So I'm going to select mass flow rate average. I'm going to go down here and select velocity average. And then I'm going to select this face that I want to measure that from. So select the face, press OK, cool deal. We have these values. I'm just going to, I want to rename it so I don't get all confangled. So that'll be nozzle mass flow rate, and then right here will be nozzle velocity. Not to be confused with night vision. Alright, right click, insert new surface goal. And then I'm going to go back here, back yonder, select this inlet face here, and then really with that, I'm just interested in the mass flow. You know what, I'm interested in the velocity as well, so I'm going to go ahead and select the same thing that I did, but for that specific face. And then the last thing that I'm interested in doing is using these metrics to get a general theoretical thrust calculation. And at its simplest form in a static test, the thrust is simply the mass flow multiplied by the velocity. And then to get that, that'll give you that will give you thrust in newtons, and newtons are just something that I don't really comprehend as well. So we're going to go ahead and convert that to kilograms. So we're going to right click on goals again, insert equation goal, and then we're going to make our little thrust equation. So that'll be thrust in kilograms is what we're going to name it. And then the expression is simply going to be the nozzle velocity. I put a parenthesis here because I'm going to be dividing everything by 9.8, so you got to do that first. Nozzle velocity, and then you multiply that, so little shift star multiplied by nozzle mass flow rate. We're going to close that parenthesis and then divide by 9.8. There's 9.8 newtons per kilogram. That's an easy way to convert that. And then we're going to go over here and just select the unit of measurement to mass, because mass is displayed in kilograms. Make everything nice and pretty. So that's cool. Now we've got our study set up. Well, SolidWorks wants you to save stuff before you can run a study. Oh, last thing, important thing, global mesh. This, if you're doing a study on kind of a complex part, it's good to set your mesh settings to like 5, so that way you can get a more accurate study. So now we're here. Cool. We made it this far. Let's run it. Bam. Run. Cool beans. And then it's going to think for a second, and then it's going to start destroying your battery in your laptop, because let me tell you what, this computational power, oof, it takes a little bit. Now you'll notice when your study comes up, it's like, what the hell, like thrust 0. This takes a good bit of cycles to even everything out. And then you'll also notice that thrust and mass flow rate are negative values, and that is because of the direction at which the fluid is exiting this part, so it's going to show a negative value, so that's okay. Now if you're wondering where I get these cool little graphs at, because at first if you do nothing it'll just show up as like a blank gray window. To get this goal plot, you simply go up here to that fancy goal plot insert and then select whatever you want and it'll show that cool graph. To get these cool little pictorials, and this is just like a heat map of the specific parameter that you choose, and it's going to show you that frame by frame. And to do that you click up here on insert preview, and we'll do an example one here. So over here in settings you select what the hell it is that you want to measure. In this example I'm already measuring pressure, velocity, and turbulence intensity, but let's say we wanted to measure, I don't know, temperature, fluid temperature. We can go select fluid, and then by default the parameter min-max is going to be what the study has seen so far. You can go through and change that to a manual min-max. Say for example if you don't care about little pockets of velocity over a bajillion meters per second, you can go ahead and refine that, and then you can go back to settings and select your min-max. Hope that makes sense. And then you can change the picture size to whatever floats your boat, select OK, and then bam, we have a super cool new cut plot, real time. Hope that helps. Yeah, you guys are pretty cool. You guys are alright. And that's about it. Alright, thanks. Bye.